Hi everyone, this is Jayashree, Assistant Professor, Department of IoT. We continue with the previous class. Okay, so there are two types of responses: steady state response and transient response. So, steady state response is that part of the output response where the output signal remains constant. Right. So, at the time when the time reaches infinity, the signal that response comes to steady. So that is the concept. Then we discuss upon effect of input RS and steady state error. Okay, what is the steady state error for step input? For various inputs. First, we'll take step input. The system is subjected to step input. Yes, ma. The system is subjected to a step input. The steady state error is controlled by position error constant. So here the error constant we are taking that is Kp, position error constant. So see the figure. In this figure, the dotted line represents the input, that is step input, the value is constant. The thick line represents the output response. The response is oscillatory like an critically damped system, right? So the input is shown by dotted line, the output load line is shown by the firm line. The equation below describes the steady state error for step input. So what is AESS? The steady state error, AESS equals A divided by 1 plus Kp. So what is an error? So it is a difference between expected value and actual value. That is my error. Okay. If I'm giving one input, step input means I'm expecting some output as a response, but it is deviating from the expectations. That is my error. So here we are calling this as a steady state error. ESS. E represents error, a steady state. So it is ESS. Next, we see about ramp input. What happens if we give a ramp input? Ramp input, you all know the input is linearly increasing with time. That is ramp input. If our ramp input, the velocity error coefficient, here we are calling that as velocity error coefficient KV will control the steady state error. Okay, so here KV controls the steady state error. See this figure, same, the dotted line represents the ramp input, the solid line represents the response. So here ESS, the equation is ESS equals A divided by KV. A is the magnitude of the ramp input. Okay, right. Next one is the parabolic input. So for parabolic input, the acceleration error coefficient Ka, it coefficient of the steady state defines the steady state error. In the same way, here ESS equals A divided by Ka. So Ka is acceleration error coefficient. So you all know the parabola dotted line represents the parabola input, right? So the solid line is the response. And what is the error? So here the error is saying the actual value and the expected value. See how the actual value is. Expected value somewhat deviating from the actual value. That is my error. Right. So effect of open loop transfer function on steady state error. Right. Open loop transfer function. So there is no feedback. It is an open loop. Okay, right. The steady state error ESS also depends on G of S into H of S. Actually, ESS depends on type of the system. So it is a type of the system and order of the system. So both the order of the system and type of the system depends on number of poles. But type of the system, it denotes a number of poles at the origin. That is, origin means 0. At origin, if there is number of poles at origin is 2, means the type number is 2. If it is 0, means type 0 system. But in order of the system, it depends on number of poles. That is, In denominator polynomial, how many s, degree of s, it gives the order of the system, right? So the type of system is defined by the number of open loop poles, it is poles that are present at the origin, right? The open loop transfer function written in the time constant form is g of s into h of s equals k1 into 1 plus tz1 into s plus 1 plus tz2 into s divided by s to the power of n into 1 plus tp1s into 1 plus tp2s. So here z represents zeros and p represents poles, right? For example, consider this is an transfer function of an open loop system, right? So the open loop transfer function, if we write this in pole zero form, so g of s into h of s equals k into zs plus z1 into s plus z2. So you have to take a t outside and s plus some terms we have to bring it. That term is representing 0, right? Divided by s to the power of n, s plus p1 into s plus p2. So here p1, p2 represents poles, right? Numerator polynomial z represents zeros. So here in this expression, n is the number of poles at the origin. It is very easy to obtain one from other. Both are same type of the system, order of the system, but there is a difference. The difference is it represents or the number of poles at the origin. That is my type number. We will discuss upon remaining in the next class. We will continue the other topics in the next class. Thanks for watching. Thank you.